Hey guys, welcome to Conf42. Thank you for joining this session. My name is Shailin Saraiya and I serve as a engineering manager at Roku. Over the last several years, I've had the privilege of leading engineering teams responsible for building and scaling large distributed systems. These are the kinds of platforms that power millions of users and they come with some unique engineering challenges. One lesson I've learned is that scaling isn't just about throwing more servers at a problem. Anyone can provision more compute or more databases, but true scale comes from making systems resilient, adaptive, and importantly, simple for developers to work with. That's really the heart of today's talk. We will explore how caching, something often treated as a minor optimization, can actually be transformed into a self healing, intelligent infrastructure component. We'll see how that shift reduces latency, improves reliability, and enables growth without overwhelming engineering teams. So let's begin by looking at the kinds of challenges that make this shift necessary. So let's start with the pain points that almost every large scale system runs into. As platforms grow, demand scales faster than most infrastructure can keep up with. Databases that once seemed rock solid begin hitting connection limits during peak traffic. APIs that were fast under small loads suddenly start timing out unpredictably. I'm sure many of you have been in situations where an engineering team spends days or even weeks firefighting, rushing to patch database overloads or trying to chase down why latency spikes during a big traffic event. And what's happening in those moments? Developers are distracted from building new features because they are stuck keeping the lights on. Traditional caching helps a little, but it's limited. They have static TTLs, those time to live settings are brittle. Data either expires too soon, leading to unnecessary recomputation, or it stays around too long, serving stale results. Scaling is usually manual and reactive. Someone notices load building up and spins up more nodes, and observability is poor. Engineers don't have the data they need until a user complains. These patterns repeat across companies, industries, and technologies. They highlight why we need caching and infrastructure that can actually adapt on its own. So, what does a better approach look like? The vision is to build systems that are self healing, that adapt, recover, and scale without manual intervention. There are five guiding principles I want to highlight. First one is self service platforms. Developers shouldn't need to be distributed systems experts. If a product team wants to add caching to an API, it should be as simple as a config change or annotation, not weeks of deep engineering. Second, intelligent systems. Traffic patterns shift constantly. Maybe a product launch in Europe causes traffic to surge at 3 a.m. local time. Systems should notice, adapt, and rebalance caching strategies automatically. Self healing mechanisms. Failure happens, a cache node goes down, a replica lags, a region experiences network issues. Instead of engineers waking up at 2 a.m., the system should promote replicas, reroute traffic, or rebuild state from logs without human input. Fourth one is comprehensive observability. Self healing doesn't mean blind automation. Teams still need reach visibility, dashboards, metrics, and recommendations so they understand what's happening. Fifth one is effortless scaling. Growth should not require a proportional increase in operational effort. If user traffic doubles, engineers shouldn't suddenly be working double hours. The system should handle the growth gracefully. This vision transforms infrastructure from something brittle and reactive into something resilient. And now, let's move from vision into architecture. How do we actually design a caching platform that supports this? A key insight is that caching works best as a layered strategy. At the foundation, you have database caches, reducing repeated query costs. Above that, distributed caches act as shared key value stores accessible across services. So, for example, a Redis is an example of distributed cache. Then application level caches hold hot data right where it's needed in memory. Finally, edge caches deliver content closest to the user, improving global performance. But layering isn't enough by itself. The design is held together by four architectural principles. First one is service mesh integration. The caching layer integrates with the service mesh for automatic discovery, routing, retries, and circuit breaking. This ensures services degrade gracefully under stress. The second is event driven architecture. Caches are updated by streams, not that means async, warming, real time coherency, and even reconstruction state from event log. Third is directory based coherency. At a massive scale, invalidating caches reliably is hard. Directory based coherency protocols help ensures accuracy across thousands of nodes. Layered strategy. By spreading caching responsibilities across multiple tiers, no single layer becomes a bottleneck. So, what's powerful here is that these principles combine to make caching not just an optimization layer but resilient backbone for platform engineering. So, static rules only go so far. This is where machine learning steps in. With ML, caching becomes adaptive. So let's look at some of the ML techniques. So first one is predictive cache warming. Instead of waiting for a request, ML models anticipate demand based on historical usage, popularity spikes, and even time of day patterns. This reduces cold start delays. Second is adaptive TTL management. Static expirations brittle. ML dynamically adjusts TTLs based on data volatility and access patterns, balancing freshness with efficiency. Third is anomaly detection. ML identifies unusual traffic, potential cache poisoning attempts, or performance degradations before they escalate. So here the impact is clear. Caching moves from being reactive to being proactive, predictive, and self-tuning. So, how do we make this work in practice? There are three main implementation patterns. First is automated pipelines. Caching infrastructure should be defined declarative, validated through GitOps workflows, and rolled out with zero downtime. This ensures consistency and reduces risk. Second is developer friendly APIs. Abstract away the complexity. Developers should be able to annotate methods or endpoints and instantly benefit from caching strategies without needing to know the internals. Third is self-healing mechanisms. Systems detect failures within milliseconds, promote replicas, reroute traffic seamlessly, and reconstruct lost state from logs. When these patterns come together, caching becomes resilient, consistent, and developer accessible. Let's talk about observability and monitoring. None of this works if we can't see what's happening. Observability is what gives developers confidence. So if we can build dashboards that could track cache or cache hit or miss ratios, latency distributions like P50, P95, P99, memory utilization and eviction rates, error rates and timeouts. But then more than raw metrics, observability needs insights. For example, detecting that cache hit rates dropped sharply after a deployment or recommending that caching a particular endpoint could cut latency significantly. Observability, if you think about it, observability transforms raw data into actionable guidance, and it's what enables true self healing. What's the outcome of all this work? The impact of self healing caching is transformative. It basically provides latency reduction, users experience faster response times across the board, database load reduction, query volumes drop dramatically, freeing capacity. Third one is high hit ratios, caches maintain efficiently even during peak surges, and global consistency. Geo-distributed caches deliver reliable performance worldwide. In other words, caching shifts from being a small optimization to being a strategic enabler for scale and performance. Now let's zoom in how machine learning actually powers caching. There are different ML techniques and briefly describe few ML techniques here. So first one is neural networks. So neural networks learn patterns in data access and predict which items to preload. We could also apply reinforcement learning. What it means is it could continuously refine eviction strategies to maximize hit, ratio, hit ratios. We could also use clustering. What it means? So clustering means group workloads or users for targeted cache warming. The benefit includes higher hit ratio than static approaches, reduced memory usage via smarter eviction, better search prediction during traffic spikes, cost efficiency through optimized resource use. Now, this this reframes caching as a continuous optimization problem powered by machine learning. Now, let's talk about the edge, where the caching gets even trickier. Extending caching to the edge introduces unique challenges. First one is coherency at scale, managed, and this can be managed with eventual consistency, vector clocks, and read repair mechanisms. The second challenge is limited resources. Edge nodes have less capacity, so dynamic sizing, intelligent eviction, and compression are essential here. Third challenge that we have often seen is network partitions. Edge caches must continue serving users even when disconnected and then reconcile when reconnected. So, by solving this, caching ensures performance is strong everywhere, not just in core data centers. So, technology alone doesn't guarantee success. Practices matter. So, best practices include self service infrastructure. What it means is developers can provision caching resources with one click, run simulations, and configure without deep expertise. The second is operational excellence, automating repetitive work, applying predictive maintenance, and minimizing toil. Together, these practices ensure caching platforms are reliable, trusted, and developer friendly. The next slide talks about the cultural transformation. So culture is the multiplier that determines success. Technology alone won't scale unless culture evolves with it. So what does it mean? First is culture which empower developers, give them ownership of caching strategies with tools that simplify adoption. The second is shared responsibility. Reliability isn't siloed ops task. It's shared across teams. The third is data-driven culture. Use metrics and feedback loops to guide continuous improvement. The Now, what is the payoff? The payoff is faster delivery, lower cost, and a better user experience. Culture is what unlocks the full potential of technology. So, what lessons can we draw from building systems at scale? Some of the lessons include developer experience comes first, simplicity and good communication matter more, feature overload. Incremental migration is essential. What it means is support legacy systems while enabling smooth transitions. Third is observability is non negotiable. Metrics validate assumptions and guide decisions. Third is expect challenges. Technical hurdles like hotkeys, Technical challenges like hotkeys are solvable, but organizational resistance and skill gaps require just as much focus. And these lessons are universal across large scale systems. Finally, let's look at where this field is headed. Near term trends include stronger ML models, GraphQL, caching optimization, and automated capacity management. Mid-term, Mid-term, we will see innovations like serverless cache functions, real-time cache analytics, novel validation methods, and post-quantum security approaches. Long-term, the vision is AI-driven optimization, autonomous operations, and intent-based infrastructure, systems that understand what you want, not just what you configure. The trajectory is clear. Caching and infrastructure are becoming more intelligent, adaptive, and autonomous. Let's wrap up with the big picture. Self healing caching isn't just about performance, it's about reducing latency, lowering database load, maintaining reliability globally, and empowering developers. Caching has evolved from being side optimization into a strategic foundation for resilience and scalability. If there's one takeaway from today, it's this: investing in self healing caching unlocks faster systems, happier developers, and sustainable growth. Thank you.